All right, so now we're going to skip ahead to chapter 12 and talk about schemes. So let me just remind you how things looked before. So affine varieties corresponded to finitely generated K-algebras. All right, and so we are going to extend this in the case of schemes by saying schemes, or rather affine schemes, correspond to arbitrary rings. Okay, and remember under this correspondence up here, maximal ideals in this K-algebra corresponded to points of the affine variety. Now, in the case of schemes, we're going to extend that a little bit. We're going to let prime ideals correspond to points. Okay, and we'll talk about the sort of consequences of that as we go. Okay, but this is sort of the idea and what the difference is going to be. All right, so let's go ahead and make that our definition. So let R be a ring. We're talking about commutative rings with 1. Then spec R, so spec standing for spectrum, is the set of all prime ideals. Of R, and it's called an affine scheme. Spec R is called an affine scheme. All right, so let's look at some examples. So let's take an example of K, where the ring is just the polynomial ring over K. All right, this has points, let's say x minus a, y minus b. So these are maximum. This is a maximal ideal in this polynomial ring, and it sort of corresponds to the point a comma b in A2, right? Okay, so those are the maximal ideals. So these are the maximal ideals. But it also has the other prime ideals. So it also has, for example, the ideal y minus x squared. This is an irreducible polynomial, so it generates a prime ideal. So that this corresponds to the parabola in A2 like this. All right, so we kind of we're seeing now sort of one of the differences between schemes and varieties. The variety A2 corresponding to this ring just has these points corresponding to the maximal ideals, whereas the scheme also has, for every irreducible subvariety, it has an extra point. Every irreducible subvariety corresponds to a prime ideal, and the scheme has points for each of those. Okay, so we'll say more about that later. Okay, let's look at another difference here. This example here, we're going to have the field K be not algebraically closed. So let's look at Rx, where this is R, the real numbers here. Okay, so it has points. And I mean the spectrum of R has points x minus a for every real number a. And it also has things like the ideal generated by x squared plus 1. All right, so you can sort of think about this as corresponding to I and minus I in A1 over C. All right, so somehow the spectrum of Rx contains not only the normal points you'd expect, so this corresponds to the point A in A1 over R. So it has these points, but it also has extra points corresponding to the algebraic closure, but they're kind of grouped together. So I and minus I are indistinguishable in A1 of R, but they're still points sort of representing them. Okay. And finally, let's look at an example of when R equals Z. So this is an example that's not really related to the geometry of varieties so much. So in this case, spectrum of Z is just equal to, well, we just have the prime ideals generated by prime numbers, right, where P is prime, or the zero ideal is also a prime ideal. All right. I don't know if I have more to say about that right now. Let's make a remark that if J is the radical of the zero ideal, this is called the nil radical. Then you can see that a spectrum of R mod J is equal as a set to the spectrum of R. Okay, so right, the ideals of R are the same as the ideals of R mod J, which contain J. So in the case where J is the nil radical, these will be the same as a set. So the idea is spec cannot see nilpotent elements. Okay, but we'll see later the ringed space will. All right, so that's coming up soon. So as a set, we can't detect the nilpotent elements, but we'll talk about the ringed space soon, which we'll be able to detect them. Next thing we need to do is define what functions on a scheme are. What are the good functions or the regular functions? So let's go back here and remember how it worked for affine varieties. So remember the coordinate ring here, ring of affine variety, corresponded exactly to the finitely generated K algebra, right? So the good functions were exactly this finitely generated K algebra. All right, so we're going to do the same thing with schemes. We would like to say on an affine scheme, the good functions are exactly the elements of R. All right, so that's what we're going to do. Here's the definition. For any point P in spec R, all right, so P is a prime ideal. Let K of P be the fraction field of R mod P. Now R mod P is an integral domain because P is a prime ideal, so that tells you that it makes sense to take the fraction field of it. Okay, and we'll call it the residue field. Okay, and then for any f in R, so we want to be able to interpret f as a function on spec R. So we'll say the value of f at P, or we could write it just as f of P, is defined to be the image of F in K of B, in the residue field. Okay, so it makes sense to consider F in the residue field, right? Because F is an element of R, so you can map it into the quotient and then include it into the fraction field. All right, and let's just put this remark. So if R is just a finitely generated K algebra, for example, this one, then R mod a maximal ideal. So for example, maximal ideal like x minus a, y minus b, will just be isomorphic to the ground field K. Right, so I think that's easy to see. And also note that if we include, so in this case you don't even need to take the fraction field, it's already a field. But we should also note that if you take a f in the polynomial ring and put it into the quotient ring, what you get is exactly just evaluating the polynomial in the usual way, right? All right, so you should maybe think about why that is the case. Okay, of course, the difference for schemes is that it's possible that the residue field could be different at different points. So for varieties, the functions on varieties were actual functions in the sense that they took a point of the variety and gave you a value in a field, and the field was the same field for each point. Whereas now for schemes in general, it may be the case that the residue field at different points is a different field. All right, so that's a difference. So for example, on spec Z, any integer can be considered as a function. So I don't know, let's say n evaluated at a prime ideal, so that would be basically prime number p, is just the class of the integer n in the field z mod pz. Right. Okay, but this is enough to define zero loci, which is what we really want to do now. So for S, a subset of R, we define the affine zero locus of S to be, so V of S for the vanishing locus of F is defined to be all the points of spec R, or in other words, the prime ideals, such that F of P equals 0 for all F in S. Okay, and just let me remind you that F of P will be equal to 0. This is the same thing as saying that the F is actually in the prime ideal, right? Because we want it to be 0 in the quotient ring. So if you use this instead, you can see that the vanishing set of S is really just the set of all prime ideals, such that the set S is contained in P, like that. All right, so that's part A of the definition. And then part B, of course, we want to define the ideal of a subset. So for X, a subset of a spec R, let's define the ideal of X to be the set of all F in R, such that F of P equals 0 for all P in spec R. Okay, and once again, we can write that in a different way as just being the intersection over OP of all P and X. All right, so using this equivalence here, you can see that these two are the same thing. Okay, now this definition seems maybe a little funny at first, but we'll get used to it. And we find that these look basically, the things we wrote down here look basically the same as our definitions for affine varieties. So, and in fact, all the properties that we proved for vanishing set and the ideal of a subset for affine varieties, they basically all hold exactly the same way for schemes. In particular, the properties that made it so we could define a topology using the V of S as the closed subsets hold. So, so we're ready now to define the Zariski topology. So, Zariski topology. So actually, maybe you're familiar like this. The closed subsets in the Zariski topology on spec R are exactly sets of the form V of S, when S is some subset of R. Okay, so this looks good in analogy to our definition of the Zariski topology on affine varieties. It does have some new features, so let's look at one of those now. So in the Zariski topology, not all points are closed. So maybe we don't see so many examples in general topology of this, but it's true for the Zariski topology. So in fact, if you take a prime ideal, a singleton set, and take its closure, according to the Zariski topology, it's going to be all the prime ideals Q and spec R, such that a Q contains P, right? So in fact, closed points correspond to maximal ideals, which we kind of alluded to earlier. So let me just scroll back up to where we were looking at this one here. So we were looking here at A2. The maximal ideals corresponded to the closed points. Those are sort of the usual points we're used to from geometry. But we also had these kind of funny points like this. So every closed subvariety of A2 had its own point associated to it, and the closure of that point includes all the closed points on that subvariety. If that makes sense. So the closure of this point here would include all of the closed points on the parabola. All right, so y minus x squared here is called the generic point. Generic point of the subvariety. Okay, in this case, the subvariety is this parabola here. Okay, and of course we can take that even farther. So 0 is, in this case, is the generic point of A2. So if your space is irreducible, then the 0 ideal will be prime, right? And so this is kind of a one point whose closure is the whole space. All right, so that's the generic point of the whole space. Also, let me just make this other remark. The residue field at 0 is the function field of A2. Right, so remember we defined the function field earlier as the ring of all sort of rational functions on A2, and that's going to be the same as the residue field at the generic point. And similarly, up here, the residue field of this ideal y minus x squared will be the same as the function field of the subvariety of this parabola. Okay, so sometimes these non-closed points, these generic points of subvarieties, are important and useful, but on the other hand, a lot of times they're not so much. So a lot of times authors will say a point, they really mean a closed point. So be a little bit careful about that. Sometimes a point means a closed point. Sometimes a point means actually any point. So I'll try and be careful and point that out as we're working here. Okay, so next I think we're ready to give the scheme theoretic Nullstellensatz. It looks basically the same as what we had before. So for affine varieties, so for any subset X of spec R, we know that the vanishing locus of the ideal of X. Oh, sorry, this needs to be a closed subset. The vanishing locus of the ideal of X is again X itself. And part B is for any ideal in R, we have the ideal of the vanishing locus of, maybe let's call this J so we don't get confused with the other, with I for ideal. So the ideal of the vanishing locus of J will just be the radical of J. Okay, so there's a inclusion reversing bijection between closed subsets of spec R and radical ideals. In R. Okay, another thing we can remember from affine varieties is the distinguished open subsets, and that will work basically the same way here. So here's the remark: a basis for the Zariski topology is given by the distinguished open subsets and those are defined as the subsets of the form D of F, which is spec R minus the vanishing locus of F, right? You can also kind of reformulate that in commutative algebra as just being all the prime ideals in the spectrum, such that F is not in P. Okay, so you think about why those are equal, and those are the distinguished open subsets, and they form a basis for the Zariski topology for the same reason it works for varieties. All right, now we're ready to define the sheaf of regular functions on an affine scheme. We have a topology now, and we're going to define the sheaf of functions on it. Now we can't quite just copy over the definition from varieties, and it's a little more complicated because we don't have a single ground field, right? So our regular functions are not just going to be functions into a fixed ground field. The codomain is changing as you move around. So it adds a little bit of extra complication. So to see what the right thing to do is, let's recall this result that for affine varieties we had the local ring of the structure sheaf. So these were like, you could consider these as function terms at A, or local functions around A. Remember, this was isomorphic to the coordinate ring localized at the ideal corresponding to A. All right. Now, this thing here makes good sense for schemes, right? We can think of this as R, just the ring corresponding to the spectrum, and then we can localize it at the prime ideal corresponding to the point. All right, so so the idea is we're going to make a definition so that these now become the local rings at a point, at the points of our scheme. Okay, so here's the definition. So definition: let R be a ring, and U be an open subset of spec R. Then a regular function on U is a family that's called phi equals phi sub p for all the points of U. So for every point of U, you have to give a phi sub p, where phi sub p is an element of this local ring R localized at P. Such that, okay, we don't want just arbitrary elements, you know, just kind of jumping around all over the place. We need some sort of compatibility condition. So here it is. We want it to sort of be locally given by quotients of polynomials, except for they're not polynomials now, they're elements of R. So for every P and U, there is a neighborhood UP, so that, well, okay, and elements F, G, in R, so that for all points of my neighborhood, let's call it Q, we have that F is not in Q, which is the same thing as saying F does not vanish at Q, so F of Q is not equal to 0. And phi Q is just the quotient of F, or G, divided by F. Okay, so every point of view has to have a neighborhood where phi is given by a quotient of elements of R. Okay, and remember this is living in R localized to Q, and this makes sense because F is not in Q, so G over F is an element of R localized to Q. All right, and just a couple of remarks. So it's not too hard to see that regular functions form a sheaf. Regular functions form a sheaf. This is a nice example of a sheaf where the sections of the sheaf are not necessarily functions, right? So far, most of all the sheaves we've seen have been, you know, actual functions on your topological space. But in this case, right, they're not honest functions because their values lie in different fields at different points. Here's another remark. The value of a regular function at a point is well defined, right? because, well, what am I saying here? I'm just saying that the residue field at P is just, you can think of it as R localized at P mod out by P RP, if that makes sense, right? So originally I defined the residue field as taking R mod P, right? Taking the fraction field of R mod P. But the other thing you could do instead is you could localize at P first and then mod out by the maximal ideal given by P in this ring, and you get the same answer. Okay, so if you take your phi P and RP and then just move it into this quotient ring, you'll get the value of the function in the residue field. Okay. All right, let's now state the lemma that I hinted at when we were making the definition. That for any point P in the spectrum of R, the local ring. Well, okay, let me just write the isomorphism. If you take the structure sheaf O spec R, all right, so this is the structure sheaf, the ring of regular functions, and you take the local ring at P. This is defined as the local ring of a sheaf, and this will be isomorphic to R localized at P. Okay, I don't think I'll do the whole proof, but let me just tell you what the map is. So we'll define a map from O spec R, comma P to RP, and how will we do it? Well, what is an element of this local ring? Well, it's an open subset together with a regular function on that open subset, some equivalence class of those. And we'll just map that to, well, what is a regular function on an open subset here? Well, it's according to our definition, it's a family like this, right? So the obvious thing you want to do is just take this to phi P. Okay, and it turns out that's an isomorphism. So I'll leave the checking of that to you. You can look it up in the notes. Well, let's do one more lemma of kind of a similar theme, this time about the distinguished open subsets. So this says that the structure sheaf of the affine scheme spec R, if you take the sections over the distinguished open subset D of F, you will get exactly, well, it will be isomorphic to R localized at the element F. All right, so just a reminder from commutative algebra, this here means R localized at the prime ideal. That means you invert the things that are not in the prime ideal. If you say R localized at one element, it means you invert F and all its powers, right? Okay. So once again, I think I'm not going to give you the whole proof, but let me just tell you what the map is. So we can define a map, RF into O spec DF. And what is it? Well, an element of RF is something like G over F to the R. And what can we map it to? Well, we can just map it to G over F to the R in RP for all P in D of F. Okay, and the point is this element here makes sense as an element of the localization RP for any P in D of F. The condition that P is in D of F is exactly the same as saying that F is invertible in RP. So that makes sense. Okay, so now you just have to check that that's an isomorphism. That takes a little bit of work, so I think I won't try and write that down here. All right, now I think it's time to look at a couple examples just to get used to the sort of things that can happen with schemes. So let's let R be equal to kx mod x squared, and I think this example might be useful in some of the exercises. So, all right, so let's let's think about what are the points of spec R. Well, there's actually only one point, right? It's just the ideal generated by X is the only prime ideal in this ring. So you can think about that. Okay, and regular functions. On spec R are just things of the form A plus Bx, right? So these are the elements of I'm thinking of these as the elements of Kx mod x squared. Okay, and if we evaluate one of these elements, so if you have A plus a Bx, and then you try and evaluate it at the 1 point x, this is sort of the same as just setting x equal to 0. The answer will just be A in the field K, right? So if you mod this out by the this ideal, you'll just get K, and the answer will be A. So one observation to make here is that functions, regular functions, are not determined by their values at all points, right? So a usual function, if you know the value of the function at every point, you know the function. In the case of regular functions on schemes, it may not be the case, right? If you know the value of the function is A here, you still don't know the coefficient of X here. All right, so how are we supposed to think about this scheme here? So you kind of want to think of it as, sometimes people call this like a fat point or a double point. Right, so remember, it's just a single point. But in this case, somehow it sort of remembers that it came from A1. So like Kx is equal to A1. And then if you look at a point at the origin here, then it sort of remembers a little bit of the infinitesimal direction at the origin, right? So it's sort of like this b sort of corresponds to the derivative of a function at the origin. So it remembers a little bit of information about how it used to be in A1. Maybe one way to think about it. We'll say more about exactly how you can think of this ring as corresponding to derivatives or tangent directions a little later, I think. And of course, this double here is referring to the fact that the dimension of kx over x squared, the dimension as a k vector space is equal to 2. All right, let's look at another example. In this case, let's look at spec z. And let's look at the distinguished open subset D of 6. Right. So what is D of 6? Well, it's just a set of all prime ideals and such that they're not 2 or 3, right? All right. So as you think about the definition of this, it's a set of all prime ideals such that 6 is not in them. So that would be all the prime ideals except for 2 and 3. Okay, and so let's think of a regular function. So let's just take an example of 5 phi could be 5/6. This is in the ring of a z localized at the element of 6. So we think of this as being an element of O spec z on the open subset D of 6. Okay, and let's try and just evaluate it at a few points. So for example, a phi evaluated at the ideal generated by 0 is just the rational number 5/6 in Q, the usual rational numbers, right? Because Q is just the fraction field of Z. Okay, and then for other prime ideals, if I try and evaluate at a different prime ideal, well, it's just, you know, the class of 5 times the class of 6 inverse in the field z mod pz. So this is for p not equal to 2 or 3. So if p is not equal to 2 or 3, then 6 is invertible in z mod pz. So this makes sense. So for example, phi of the number or the ideal generated by 5 would be 0 because we're landing now in z mod 5z. Whereas if you took a phi of say 11, then you'd have the class of 5, and then 6 inverse would be the class of 2. So that would be equal to the class of 10 in z mod 11z. Okay. All right, so I think we'll call that good for today. And in the next lecture, we'll define morphisms of schemes.